artist when he just graduated, where he made several revolutionary contributions in wireless communications and using information theory to characterize the performance for wireless systems. And Li Zhong has won several rewards. And one of them was the Best Paper Award, very prestigious Best Paper Award in Information Theory Society. So without further ado, so here's Li Zhong.
Thank you, Yingbin. First, let me say it was really a happy visit. Thank you for organizing. Thank you everybody to meet with me, and I was at this number of really interesting conversations. You know, when you visit anywhere, you always hear, "Wow, look, they have a better group than we have." Right? So, yeah, I sincerely think that. It was very effective. And because this talk is sort of long, I will just jump directly into it. This is the title. You don't have to worry about how I organize this 3 words. It's learning, feature, and geometry. These are the topic of this. Okay? And I do want to mention my postdoc Xiang Xiang, who is the co-author of this entire effort. We started to work together like 5 years back. And now he not only can do the work very well, he is actually preparing for a run. He become a better runner now. This is a 10K run, but now he can do half marathon. So this is a good thing, right? So let me start the general picture. I like to start to say that most of the learning and inference problems, we should talk about them in the language of feature functions. Feature is what we mean by a function. I see some input, you would like to apply some function to evaluate on this input, and then that become a number, and then you process based on that. The simplest case is you are trying to use X to predict some Y with a known model of this conditional distribution. And in those cases, for example, if Y is binary, we can hear somebody.
I'm sending a message for the person to mute.
Maybe you want.
Can you mute yourself? Oh yeah. Yeah. You're student too. So isn't that your student? So in the simple case, that's we know the best feature to take is likelihood ratio function between the 2 hypotheses, right? Two values of Y. So that's the easiest case. More general, you would hope to do some processing of the data to take the sufficient statistics, and then based on that to do your prediction. That's it. That's the gist of all signal processing courses, the classical ones. And nowadays we face big data where this kind of getting sufficient statistics gets hard. Well, we still follow the same principle. Basically, you want to choose these features such that these features carry information as sufficiently as possible. So that's a notion of carry a lot of information. That's it. But these are all happens when you know the model. And obviously, in the learning case, you do not know the model. And what do we do in this case? We try to use the data to learn the model. The typical thing to do is to think of a parameter estimation problem, right? You will find some data, and you believe your data live in some kind of a parameterized space parametered by this parameter theta, and then you try to find the theta to match, to fit that data. And the best thing you do is ML estimate, for example, to minimize the KL divergence of entropy loss and fitting the empirical distribution into a given form. And a very commonly used form of this parameterized family where you want to learn your model from is exponential family of this form. So they take this, the theta, your parameter come into your model in this exponential way. And in this, you see, oh, there is a thing called fx. Right, so that's the feature. That's the feature. That's what's called the natural statistic of this. And when you solve these kind of ML estimate, what you do is you find the empirical average of these feature functions, try to match that with one of the models. That's how you do ML estimate in this special case. The point is, The point is that you process your data by evaluating this function or feature function into your data, and from that you do your learning business, right? So then the question is, where do you get these feature functions from? Well, sometimes if I give you this parameterized family in this form, that's the natural statistic you apply to the data. Sometimes there's other operational reason to choose certain feature functions, like there's some kind of pre-processing that's in your system. You could be quantizing your data, that's applying a function to your raw data. You could be doing some smoothing, some kernel. There are many reasons to put in some feature functions. And in these harder problems, you might have some rule-based feature, right? I like to recognize the people in the base. How big is the nose, right? So that's rule-based. There's some expert tell you these are the good features. The whole point of these two slides is to say these learning problems are related to features. And in both examples I was giving you, the previous one, the model. This one is the model to some level with expert knowledge. People tell you what feature you should use, meaning what function you should apply to that data. And well, I have harder problems that I have no idea what kind of features we do. That's the generic problem, learning problem, where I do not know what to do with my data. I don't know. I don't have any idea what we do. I apply a neural network. Right? That becomes like a universal solution. This is my really ugly neural network cartoon, right? So X coming in, many hidden layer, whatever way you connect them. And I'd like to put attention to the last layer, where suppose you have K nodes in this last layer. And think of what you do in all these previous layers. You are trying to come up with a pre-processing of X. Output of these are all functions of X, and we call that feature functions. And you are making decisions of Y based on these feature functions, right? So neural network is one way to prepare these features. I didn't add anything new here. It's just a different language to talk about the same thing you're familiar with. And hidden layers, all of those structures, what they do, they kind of give you some feature functions. And these feature functions, all of those things, you optimize the weights, that's parameterized in a collection of feature functions. That's what it is. And you have all these big literature to say, what kind of feature I can generate with this network? What kind I can generate? That's the expressive power of the network. Right? There is some limitation of what kind of features you can choose. And the general picture I like to put out is we should sort of separate how you generate these features from how you use these features. This is a sort of a more modern way of using machine learning, like meta learning, right? Like multitask learning, where we would like to generate these common features. Then depending on which task I want, I will find a different way to read out from these features. And yeah, so that's it. And if I got a transfer learning, a changing, a time varying model, then basically I train these features from one task. Now when I move to a different task, I read out a different task. Right. So the only point I'm making here is features are important. Right. That's it. That's what we're doing. And so this is the conceptual thing that we want to put out. Is we would like to have a feature function centered view of all of these problems. And yeah, so there are a lot of need to decide how you do pre-processing of the data. So for dimension reduction, there is a goal of boosting these features. You want to keep the information. That's the general, right? You want to make it informative. You want to get rid of irrelevant information. These are all intuitive statements. And the question is, hey, can you put a number on these goals, right? If you think about it, maybe not that much at this point yet. And well, good news. Neural network, because it uses so much, is an efficient way to general these feature functions. And well, if we would like to do one more step to say, how do I do this better? How do I design better neural networks? Well, maybe we should understand what feature we want. Right? How do I even say which feature is better? So there is some kind of, I would say, good research started from complaints. Right? This is a whole bunch of complaints we have when you use neural network as selecting the feature, you have some difficulty. One of which is this big black box thing. If you train K features, that's K nodes on your last layer, you got these features. And you say, with this, I can predict something. But then these K features come to you as a whole, you can't separate. I say, hey, well, I can only afford to do K-1 features. You train a network with K. Which one do you want to take off? I don't know, right? There's no way. You can't arbitrarily take off one without, you don't know which one is less important. So basically, there is no way to figure out which subset of features are doing what. That's the way you operate on. You cannot combine with other information. Suppose there is a guy coming in to tell you some side information. You say, well, that should help me to reduce the requirement of all of these features. Well, you can't, because you train it, this K features are used together, can't make any. It's a black box, can't work. So really what this says is we do not know how to measure whether a feature is good. If you think about it, the only way we measure whether a feature is good is from, can this feature help me to reconstruct or to predict, right? So that's a task-specific metric. So we're borrowing that task metric, whether you are reconstructing your label, as a way to measure, are these features good? And we're not talking about these features, we're talking about the batch task. We're borrowing the metric in there. We can't really say which feature contain the useful information, right? And obviously for the same reason, you can't, this is the difficulty of applying deep neural network in engineering discipline. You can't incorporate any other external knowledge. Say this feature function better be symmetric. Well, what do we do about that? Right. So there are a lot of these external knowledge, the domain knowledge we can't do. Right. So this brings us to this talk. This is what we want to do. I'd like to propose a geometric way to address these feature functions. And based on that, we would like to come up with a way to measure, what feature functions are good, and hopefully to say that the common learning algorithms, are they learning the right feature based on our metric? It turns out they are. We better, one of the claims is that the neural networks, the generic term, is learning feature in this way. Right? So that's consistent with our metric of how informative is the feature. And then based on that, we say, well, if you know the metric of this, you probably have better way of using neural network, right? Then we're going to propose a couple of extensions of how to use one of them called H-score, one of them is called nested H-score, and I'll show you some nice algorithms that we can push out that's based on this general approach. One of the things that I'm going to do is a interesting. If you want, this is exactly an inference problem with a side information. And at this point, what happened? I guess at this point, if you know side information is an interesting problem, very good. Now you should appreciate this is a nice thing. Otherwise, when I get to there, I will tell you why this is a significant problem. This is actually a problem we extensively studied in network information theory. So this is related to a lot of literature. Yeah. So let's go ahead. So these are the 5 sessions that I'm going to do in here. First one, let's talk about a little bit of a mathematical structure. I want to talk about features. What features are? They're functions. Functions defined on the same alphabet, right? Function, we use this. All the features are functions. They form a space. And when I have a space, what I would like to do is I like to build a little structure. This is the structure. I like to define in the product between 2 feature functions as the correlation. There's an expectation of the product of the 2 functions, where I plug in these x with a given px distribution. This is the definition. You have to check this satisfy all the requirement of being a valid in the product. It does. Now you should have seen this in a classical learning estimation problem, right? Orthogonality principle is proved using this inner product. And you should observe that this inner product has one little thing that I would define this inner product based on a reference distribution. So all the rest of the talk, this geometry has a reference distribution. Don't ask me how to choose them. Different problems you have to choose them differently, but I'll show you a few examples. And well, this defines within the product, you can define norm. That's precisely the variance of these feature functions. So with this, now I would think each feature function is just a vector in the Hilbert space within the product defined. Right. Well, if you change the reference, I might have to change the entire space. Let's don't do that. For each problem, let's decide what's the reference. And after that, well, what do you want to do? Well, we probably could define more complex operation in these feature space, like a projection, right? So if I got a feature function, I have a subspace of other feature functions, linear combination of the other, I could write, hey, what is this projection? So this picture you're going to see many times. Once you define inner product, all of these projection can be done. That's well defined, and it's this minimize some kind of norm. It's an optimization now. And I'll show you that this projection operation is important, and I'll show you how to do that and different variations of that, right? So this is really the geometry of this. Now let me make this jump. So far I've been trivial, right? Now let me make this a little more interesting. If you're willing to define feature function this way, now let's look at a function in the space of joint x and y. We would like to talk about the joint distribution between x and y. That's, I'm just changing the alphabet. Nothing actually changed. This would be a member in here would be a function of both x and y. I like to say, well, there is one kind of a function that we are really, really interested in, which is a function of both x and y, but take this product form, fx times gy. If you want to write this function over x and y, if you think it's a finite alphabet, you use a matrix to write this function, right? Each value is f of a particular xy pair. And this, if it takes this special product form, that means it's a rank 1 matrix, like fx times gy. So it's a product of two functions. We like to, particularly take this out. We use this this symbol as tensor product. We like to take this out. So these are a particular kind of joint function we like to put our eyes on. We call this rank 1 functions because they correspond to rank 1 vector. Now the thing is that any joint function, arbitrary function in the space, arbitrary matrix of that if you want, I can always write it as linear combination of these rank 1 products. That's if you think of this in the matrix way, then it's kind of obvious. I could always get this into get any function in here into a sequence of this fi times gi. I can always do that. And what we particularly want to say is, well, let's do a so-called rank 1 approach. You give me a function gamma is a when state. We like to approximate with some kind of f, g, and a scaling factor sigma, right? To make this minimize this norm. That would be based on this norm. By the way, this norm was defined with a reference distribution, right? Let's say we choose one. And within this norm, I like to say, hey, what is the rank 1 approximation of any given function? We like to give this whole operation a name, because that's zeta. You start with a function, then this one tells you a rank 1 approximation is the level. Right. So that's nothing. Again, still, it's kind of a smooth thing. I like to have any function. I like to say, let's just do rank 1 approximation. What is the best product for approximation of this according to this norm? Yeah.
Quick question. So is it obvious that any function can be written as countable sum of rank 1 function, or?
Well, it can be approximated as it can be approximated, right? You need the function to be L2. You need to have some kind of a convergence requirement. And in our mind, we always think of this x, y as discrete finite.
Oh,
then you have
it's
no
obvious.
problem, right?
Then
If it's a continuous alphabet, let's say we quantize it, right? So let's allow some baseline process.
These are just like matrix operations.
Exactly. Right now it's all matrix operation. We'll see how this gets interesting. Very good. Thank you. This is linear algebra, right? Nothing special about this. This get out a little bit. Well, we do want this F and G to be, because it's vector, why don't we make it union? So that's a standard form. So that's where the sigma thing come out. If you optimize here to make sure these F and G are union, then you like this easier. Yeah, and now obviously we would like to do many orders of this. So you start with a join function, you do one rank one approximation, and the remainder another rank one approximation of this remainder and further remainder. You can do this sequentially for whatever k wrong, right? So this is the statement for any function. You can write it as a sum of k rank one matrices, right? So that's the first k rank of this, and add a remainder. Obviously, the remainder gets smaller and smaller. That's how any convergence could possibly happen. And each one of them, suppose they are standardized, right? And the goal at the end is to say, well, let me restrict myself to this case order, rank k approximation of the given. That's, it's, again, all kind of not hard. Only a little thing that come out is that you should think of this minimization as finding a projection for rank one function, then whatever is remaining is orthogonal. So this guy is orthogonal to the function you choose. So there's a sequence of orthogonal. This is very similar to SVD, right? The next rank is orthogonal, and you get this order because it's orthogonal. Also normal basis come out. That's very cool. Yeah, now let's really apply this, right? So that's the mass setup. Let's apply this. We would like to do what? We would like to do this low rank approximation to the dependence between two random variables. We would like to say, hey, what is the easy way to say how X depends on Y? And to do that, we take this what's called a pointwise mutual information function, which is log of the joint distribution divided by the product. You can also approximate this as the difference between this divided by this, right? So that's just a Taylor expansion of the model. Right? We would like to think of this as a joint function over X and Y. You can put X and Y in here, that gives you a value. Then this defines a PMI function. This is the only function we would like to do low rank approximation. Why do we care about this function so much? You see, this is the difference. This difference being 0, that's when X and Y are independent. Now, whatever difference is to tell you how X and Y are dependent. We like to decompose. We like to have a low rank way to describe this. Okay, describe how X and Y are dependent. There's some technical part of this that I need to make some local approximation statement to do some statement, which I do not want to do in this talk. But let me tell you what are the statements I would have. Is if I choose this Px, Py as remember I need to choose the reference. If I choose this product distribution as the reference, then it turns out that norm square, that inner product will use a norm square of this joint function. That can be approximated to it really is a good approximation to the KL divergence in second order Taylor expansion. So basically that says this function, if I look at its norm square, is directly related to mutual information, which measures how much does X and Y depend on each other. If this thing is large, then X and Y has larger mutual information, they strongly depend on each other. And this is a lot stronger statement. They're like proportional. This is the same measure. That's the claim, right? So this is the I wouldn't prove this or even state why this is correct, but just take that as true. Right? So this PMI function tells you the lumps of that, tells you how much X and Y depend on each other. Why is this off a little bit? Yeah, too bad. Now let me read this. This basically says I would like to approximate the PMI with a low rank approximation with this norm square we define, picking this PXPY as the reference. And the claim is that norm square corresponds to KL divergence or cross entropy loss. Yeah, so that's another statement that requires this local approximation. I'm not writing the mathematical statement here. Now let's try to say, let's approximate the thing. I like to approximate the dependence with the first K of them. Obviously, I choose the strong ones. Why do I like this? Why do I like this? Well, first of all, this is doable. Now I have those projections. You can do them one by one, just like an SVD. Yeah.
So the first K are the one you showed before, where you took the kind of the difference and then the new one.
Yeah.
Like a gradient boost type of thing.
Oh, I would. That's SVD. You can do this. You can get the first mode and then delete it and do everything also in that second mode. Right, and it's not really gradient. Right?
No, I know. I mean, gradient boost in anyway.
Yeah, I guess different terminology on the same thing, right? So we can do this. We can do this. There is good algorithm to do this. Let's start with that. And now, if you think of this, why do I really like to write PMI in this rank K form? PMI, remember, defined with the log of PXY divided by PXPY. So this basically says, well, if this is precise, then that joint distribution can be written as the product distribution times exponential of this sum, which is a nice form. And if that happens to be true, you know exactly what is the sufficient statistic. These F1 to Fk star is sufficient statistics. So meaning if I can make this rank K approximations, I know what to do. This is my sufficient statistics. That's my best feature I would put up, right? So that's the statement. This turns out to have a large statistics literature. People call this HGR Martin correlation. This is related to Wiener contribution. There is a whole literature called the correspondence analysis. I'm not going to go to any of those. The HGR stands for Rainey, so that basically tells you this goes back to 1930s. It's a very old topic. Now, this is important. What's important is, now remember this guy, the norm of this PMI is mutual information. It tells you how much X and Y are dependent to each other. Now with this, I'm approximating it into this K orthogonal mode. It's like an SVD operation. And that made this PMI to be approximately the sum of these sigma i's. So this actually gives you a very strong statement. It says that X and Y are dependent through these parallel orthogonal modes, one by one. F1 is dependent to G1, F2 to G2, F3 to G3. So the dependence between two random variables is not a single number to describe. It's a whole spectrum to describe. That's the story, right? So you can't say one is stronger than the other. And yeah, so now this obviously is a nice mathematical structure. Let's see, how do we learn these things? How do we learn these feature functions? Now the claim is that there are many algorithms that can be used to learn these modes, these feature functions, these low rank approximations from data, particularly neural network is doing that. The statement is that a neural network, what do you want to design this thing to do? You want this to find a k-dimensional feature that carries as much information as possible to predict these random variables of y, right? So in some sense, this is exactly the same thing we are talking about, having a low rank approximation of that dependence, right? So intuitively, they should do the same thing. Where is gy? You can see the fx, right? Where is gy? Well, the way to read this is to think of y equal to 1 has a whole bunch of so each of these y equal to 1. So this, if we're doing a classification, these are different values of y. So if you look at the branch out from this node, there is 1 to y equal to 1, 1 to y equal to 2, 1 to y equal to the other. So it is one value for each y. And the weight on these fan out, this set of edges, is a function of y. And that's G1 of y attached to F1 of x. And then there's a G2, so meaning these G function you actually can read from your last layer of neural network after this train. And when that happens, you end up you solve flags to get a set of function that's exactly of this form fx and gy, except they're not normalized. So there isn't any effort to make them minimal. It doesn't matter. Okay, so that's it. That's how these are related. And well, it turns out I also argue that this norm, this projection minimizing the norm difference is exactly the same as cross entropy, minimizing cross entropy loss. So that's really the intuitive reason why when you train the neural network, you actually learn this stuff. You actually learn this model decomposition. Is that true? How do we know what to think, right? So at this point, you almost should be thinking, oh, I can do an experiment. Well, good news, we have done that for you. This is an experiment. So I'm going to later give you a link on all of these demos. If you train a small data set over a small, very expressive neural network, and then because you know what data you put in, you can actually do that SVD. You can take out the first mode, you can get fx and gy, and then you can go ahead and read those stuff out of what training converts to. This is a product. I have the code online. You can try it out. So this is an interpretation of what exactly is being learned in neural network. It is learning this. Yeah.
Well, very interesting.
Yeah, see, that gets more interesting things are coming. Yes.
Do you get unique ones like F and G?
Well, the neural network probably scale this. While you normalize it, then you match it to this.
Just the difference is just the scaling.
Yeah.
Otherwise, it's the same.
So far, I only have one function.
Okay.
Yeah. So I only have one function. So you just take the top one and give it back. Yeah. Well, this is the line that's almost hidden. If you talk about multiple pairs of feature functions, now you got a problem, because a neural network tends to allow any linear combination of these feature functions. Because if you do a linear combination, you just undo it from the G side. So meaning the neural network does not do one by one to your singular vectors, but what can be shown is it would give you the linear combination of the top K modes, right? So the K things they learn are actually a mixture of your top K singular vectors. And then that's why you don't know which one is which. That's why you can't separate them. Yeah, is that clear? Right. So that's it. So that's exactly your question. Neural network doesn't have a unique solution. Everything of them is the same. So that's why I give you a mixture of them. And if you just train a normal neural network concept. Right, let's continue from there. This is getting a little interesting. This is getting a little interesting. We're making some claim what neural network is doing, right? Okay. Now we like to say, well, now we know what to do. What do we call a good feature? A good set of feature approximate that potentials. Well, under my norm. Yeah. Well, then I probably have better way to do that than neural network, which is what we call H-score. If you think about it, what this rank one approximation is, I take the PMI, try to augment this norm square, right? And well, in general, if you want to do that, you can't directly solve this because that would require you to know the PMI. I do not know the model, so I can't really solve this. So here is a way called the H-score. What we do is we say give two feature function. We like to define this thing as the H-score. One half, who cares? PMI, we just basically subtract this error. Yeah, subtract this approximation. This is PMI of your real model, right? So you could right away with the definition say minimizing this is the same as maximizing my H-score. That's obviously because this PMI is fixed. Right? So I add a fixed thing. That didn't do anything, but good news is now I can open this up open this out, this PMI square business actually got canceled. And you ended up to see this H score turns out to be of this form, covariance of this fx is two feature function, fx and gy, and minus some things in here. Why is this a good business? It's because these are all of the form of average. And when I do not have the model, I can when I do not have the model of this, I can do an empirical average with my data set. So this particular H score is a good thing that I would with whatever data I can just plug in to do that. And I already said that this optimization minimizing this norm square is exactly the same as maximizing my H score. My H score now can be evaluated from data. Let's do that. Yeah. So this is the step, right? H score of this form, and do that. And the good thing is that we only have data, not model, we just do the empirical average. So that's the approximate version of this. And the so-called H score network is of this form. I got an X, do a forward neural network, generate a function of fx. I got a Y, got a forward G of Y, and then this F and G got fed into this box to evaluate the H score. And then I try to maximize this by back propagating, train this neural network and this neural network. Okay, just back propagate and take out. That's a H score network. We have code on this tool in the demo. Now, so that's called a H score network. You could argue that what we did was basically it used to be X forward processing to give you Y. Now we got this Y part turn around, feedback, right? And then we train these two neural networks. This is sort of an equivalent statement. There's a question. Yeah.
So in classification, we have multiple data products, so that kind of like belong to the same class, which means Y will be the same. So you will input into G's and you will get the same thing for different.
Then that's how it is.
Issue here.
No, we don't. Then you should be classifying them into the same thing, right? Then that's okay. So this basically is the same way as you train neural net. You got X, you got Y, just put it in as a batch.
Okay.
Evaluate this, back propagate, then do a few rounds. This converge. You got fx and g, right? Right. See, that's a general picture. Yeah.
So F is your first hidden layers, like.
Well, it doesn't matter what kind of network this thing is. It's just a forward network
and G is your last layer weight.
G now, see, that's very important. At this point, this G, I don't have constraint on that anymore. It used to be the last layer weights. Now I don't have constraint on. Right, I do forward processing, right? Yeah, see, that's exactly the trick in here. So what is good about this? If this G is a categorical, if this Y is categorical, I do this G. This is precisely the same as the last layer weight. But now I don't have to. I can have Y much harder. Yeah. So this is the important message. What is good about this H score? Well, one thing good is now fx, gy, you can both read out. Accessible, right? Accessible and controllable. If you say, hey, I would like this function to satisfy this constraint, make your network to have that constraint built in. Right? So this is doable. Another thing is I didn't even worry about reconstructing Y. Yeah, so the metric is on how fx and gy's are correlated, are having strong dependence. This is a metric that doesn't require reconstruction of Y. So that's another conceptual good news. And this is forward process of Y. If Y is not categorical, suppose Y is an image or it's a sequence, I can apply CNN for image and what RNN for sequence, then that sort of use the structure of Y itself too. Right. So these are all the good news of this. That's very nice. And this is just another example. Suppose I freeze one of this F and get this G. This pull us back to the projection story. You should review this. I have a PMI. If I freeze this F, that limits my cross function to be in this linear space. If I freeze one of them, I just cross the other guy. Then when I optimize this is really finding the projection. And so if I hold one side of this unit, I ended up getting the projections. Yeah, so these are all, a flexible use of the H-score network. Yes.
So what if we fix G as identity map? Where
then you're training this with identity map, right? So you're projecting fx into that. You can do that, right? So this is a good thing of this. You can freeze whatever way you want, and at the end you may not have a good approximation, right? But that's the best approximation under whatever you freeze. Yes, very nice. Okay, now I'd like to, now we have built this, I'd like to do something that I couldn't do before. I like to do something, well, I sort of can do, but it's pretty uncomfortable, right? So I like to do this problem. I still want to do this feature selection with XY data set. But I now want to have a constraint that this chosen feature function is orthogonal to F bar. F bar is given to you. Orthogonal in my inner product, meaning F times F bar average over E Px is 0, unquote. I just give you constraint. Well, you can think of what kind of constraint it is. I want to make sure my chosen function to be symmetric. And there is a function that this function has to be orthogonal. Right? So it's these kind of things. So this becomes a constrained optimization problem. Got a constraint on F has to be orthogonal to a given level. How do you do that? Well, you see that's easy. I can put a regulator at the end of this, but regulator is a painful thing. You put it in, then how strong you want to put in the multiplier, not clear, and it could pull you away from your objective. I like to not do that. I like to do a projection. So this is the cool part. So what I do is I can use I don't want to do that, right? I don't want to do the regulator. What I want to do. Well, I have another way to do. You can give me a network structure that can generate F function that whatever generate out is orthogonal to F bar. But that would require you to change the network structure. That's also kind of an undesirable approach. I like to use the projection I just developed to do this, nicer. I want to make it look like the previous optimization without a constraint. Now here's the idea. Here's the idea. I just said, if you freeze this F bar, optimize over the corresponding G bar in the previous problem, you're making a projection of PMI to the subspace of everything multiplied to F bar. Let's do that. After you do that, you look at this error. This error is PMI minus that F bar times the corresponding best readout from F bar. You get that? And once you have this, you realize, well, that's orthogonality principle. This red vector is orthogonal to anything you can express with F bar. Oh, nice. I got something orthogonal to F bar already. How about I just use this as my target to do my unconstrained, low rank approximation. Yeah. So now let's see how that's done. I would basically want to take this red thing, do a rank 1 approximation of that. What is this? Well, put this thing in. You basically want to find F and G such that it's a good approximation to this was the red business. What this really is to use the sum of this guy and this guy to approximate the original PMI. So meaning if you can find the FG that paired up with F bar and G bar, do a two-function rank 2 approximation of the original PMI, that give you exactly the same answer as this. Yeah, so that's really the nested idea that Xiangxiang came up with, and for that you need to come up with the two-function H-score, which it used to be covariance expectation, now this become covariance sum up, expectation sum up is slightly more general than before. The point is this can be evaluated still from data empirically. And now let's do this. I would like to solve this constrained optimization. Now I turn it into this unconstrained optimization with more features. Now let's see how we do that. We will start by training this, freeze F bar, train this G bar. That gives me the optimal choice of G bar star. Yeah. After that, I freeze this network and I put this in here. This is the notation Xiangxiang came up with. I got this function come out as a two-dimensional. Let's just put them together as a vector. Usually people draw this graph with a dot, right? This has become a vector. Now this two-dimensional feature, do a two-dimensional H-score optimization. Then what you get is this F orthogonal result. And guess what? We're not going to do this, right? We're not going to wait until one network converge and try another one. But why don't we just do them together? Right. So what we really do is to let us free, get data in and optimize these two H-score together. Just let it run until we converge and story. Right. And it turns out you get the orthogonal, the one with constraint. So this is one network. Oh, that's kind of a little bit interesting now. Now let me tell you why this is a useful business. We call this nested H-score network. Let me do this repeatedly. I got a PMI, right? I would do a single one function H-score. Optimize that. I let this free, let them do. This is the best rank one approximation of the dependence. This is the thing we can get with that little demo. Then I freeze these people and feed into a concatenation, try another pair, F2 and G2. And this is a two-dimensional H-score. Now this helped me to get the second pair of feature functions. Oh, nobody's going to stop there. The third one, the case one. Yeah. Well, even though I was telling you this by train this, freeze this, and then train this, freeze that, train this, I was telling you in the sequential way, nobody does that. Train them all together and wait until they converge. This is why I need a convergence analysis, right? But let's say they converge. We did this experiment again in the demo. This does what? This gives you K pairs of features. Well, this is exactly the same K pairs of features if you do a forward neural network with one added advantage. Is now I know the order. This is the most strong, useful one. This is the second. This is the third. Now, if you say, hey, I like to kill one of them, kill this guy, right? Because that's the least useful in your prediction. Right now, I train one network. You can use it in a variety of functions. Right. So this is really just to some extent it's a functional SVD. Right? Nothing special. Nothing predictable. Okay. Okay. Now I'm going to do an even harder problem. This general approach can do a lot of harder. This is the side information problem. I'm imagining you're going to process this X into a feature function and give to a inference predictor part, but this predictor has a side information of S. But this is a model that information series like to use. But in the current literature, there are many different ways to think about it. You can think of this S as a index of different tasks. And this is just a representation learning. You want to represent X into a k-dimensional fx. And depending on different tasks, you want to have a different way of reading it out. There is a constraint that your S has to be finite number of multitask, right? One task for each readout, right? So that's what we talked about the whole day yesterday, right? So that you can think of this S as a time varying, then you have a model that keeps changing. You want to learn a feature, and depending on time, you want to evolve this result inside, right? So there are many different things in here. Here, I like to think of this as more general, anything. In fact, in our experiment, S is a sequence, very long one. You can't really have a clear count of which one is which, right? So this is not a necessary categorical. So we really would like to apply some flexible operation on this. Yeah. Well, the formulation is that I really would like to save on this feature function. I really would like this feature function to be small. So think of that, I have to transmit over communication link. K-dimension, let's say, no more. Even quantized maybe, right? So that's the That's the whole picture. And intuitively, when you choose these feature functions, you have one goal. You want to use this to help you to predict y, but you want to make sure whatever S can provide, let's don't talk about that. Let's choose a feature function to avoid its dependence to S, to the side information. Right? So you're steering the contents of your information. That's the idea. Now to do that, let's build our vector space. We will think of the drawing function of 3 random variables. Now this is a little bigger. I'll take a reference of this form X and S and Y. I'm looking at this X depend on S and Y together. So let's say I take that as my reference. This is mathematical sense. And what I would like to do is I basically want to decompose the dependence between X and the pair of random variable S and Y. I like to do that decomposition, which I write out this PMI X to S comma Y. It's of this form. I like to make a decomposition. In particular, I want to say, well, which part of the feature of X depend on S? Which part is that conditional business, right? Is that, that you could use not repeating S? That's really the concept. So this, we like to distinguish two-part information. Which part of X is about S, which you do not want to report? Which part is about Y in addition to S? That's the part you want to use this F to report. You want to do model decomposition. What is that? Well, if you think about it, there is a nice projection story again. I like to think of this. This is the PMI of this X depend on SY thing. I like to decompose it into two subspace, one of which is what we call the Markov component, and the other one is the orthogonal component. Let's see what they are. Right? This Markov component is one that I like to approximate the PMI with the PMI hat. That's a approximate model, but this model satisfies this Markov condition X depend on S, depend on Y. Given S, X and Y are independent. I basically want to have this model to satisfy Markov property. Once I have that, what happens? Think of this component is what? It's a Markov model that the dependence of X to this pair S and Y only goes through S. Yeah. This is that pi m. You can say that corresponds to, remember this norm of a vector correspond to mutual information. This mutual information is just X to S. I used to be having X and S and Y. And now I got this piece out. The remaining part is the conditional part. Is how X and Y are dependent given S. That's exactly the problem I like to do. Oh, nice. What I do is I would like to take this red vector, do a model decomposition on that, take the top K. That's the function I like to use. Right? So that's the solution to this side intuition. Hey, let's do that. Right? I got this. I like to make a prediction for this pi m and take out the other thing to do my model decomposition. Wow, I just did that projection operation. Let's do this. Let's first take this X and S, train them. Let's call this F bar and G bar. Yeah. After that, I can freeze these two things, concatenate them with another F, another G, but this time I'm talking about S and Y put together. And yeah, and then put these features together, do a two-dimensional or whatever, increased dimensional of each. So this result would be well, depending on how many functions you allow, this would be a low-rank approximation of the conditional component. And with that, that's the thing you use in your the side information feature selection problem. Yeah. So this problem, well, I can probably make one that's a little bit harder to do in the current literature. Right? So we're making some problems that is not trivial with a direct application of a bigger neural net. We want to create this functionality, and here is an example. Yep. All right. My time is very much up, right? So let me put out some good timing. Some conclusion. Let me say what are the statements that I'm making. I'm making one. The first thing I said was we should understand these problems from the feature processing feature function. And to understand this, we need to have some kind of a metric. What feature is good? How do I operate on feature? And to do that, let's define in a product, right? And the corresponding norm as the information value, right? So this answers the question, how good is a particular feature? So that's sort of answer. And we need to enrich our capability to do feature space operation. And I think this nested edge score invented by Xiangxiang was a good operation, was a good axiom level of operation. That if you can do projection, you actually can do a lot of funny things. And that's cool. I like to, more importantly, list all the open problems I want. This is why I'm here. Right? That I want people to work on. I have a whole bunch of them. Well, obviously, all I did was let's train like a number of H score together. Which one converge? How many samples? Does it take a lot? You can run some of our demos. Turns out it doesn't take a lot of samples to converge. It's pretty fast, but we haven't even made the effort to prove that. There is an intuition is that when you are training on this model decomposition, those strong modes converge faster. So it's exactly the ones you want first find out you can converge. If you try the weaker mode, they actually take longer time to converge. Longer time meaning more samples to train. So this is actually a good thing. The part you want converge fast. Nice, right? So that's why we could handle this large data. And so that's one question. And prioritize processing this. So basically, this was the project we're on. I'm hoping that after you decompose this, you can know which feature is important to carry a lot of information. And when you transmit this, you can prioritize. Right? So there is clearly a network protocol that should be based on this kind of training result. What feature is important, or some kind of control mechanism that's prioritizing on the more important ones. I made this orthogonal business trying to get rid of the dependence on S. Well, that can be generalized to a secrecy state. That's another topic we want to talk about, right? You do not want your feature to depend on that sensitive information. Oh, I know how to do that. Project it out, right? You can learn that saying on the run. This is doable. And I only give you 3 random variables, right? X, Y, S. This turns out this multi-terminal dependence, multi-random variable dependence is a pretty interesting thing. You first have to separate this into the information shared by this 2 or this 3 people share some information. You first have to separate them into different pieces. Then you do your, low rank approximation. So this leads to a lot of nice networking efficiency problems. Maybe we should revisit. Okay. So that's all the wish list I have so far. And it's also the end of this talk.
Good question for you. How about H-score networks relevant, or how resistant are they to overfitting relative to more conventional ones?
Well, we do not know, right? We have experiment on that. But by the way, let me do one more thing. Okay, this is the GitHub page of all of our blog and demo on that. I used to have a QR code, but take a look. It's very readable. It's supposed to be simple, and the code are all in Jupyter Network. You can go in and play with. Now, I do not know. I do not know, but I have no reason to believe they are worse than when you have categorical data where H-score is equivalent to a normal neural network. I have no reason to believe they're different, right? And when you have harder data,
Well, any potential theoretical advantages for overfitting relative to more conventional architectures?
Yeah, so it's a very, very good question. We, it's still an active research on why neural network is gradient descent somehow can beat these overfitting business. Now, what we're doing is your old neural network, the big chunk of that to generate F is still there. what this is pushing is, let's put it one on the Y side too. I guess maybe more of that should be better, right? There's no clear reference to these things. I would imagine those protection against overfitting should be roughly the same as what we see right now in practice.
Well, would you say that H scores, because you can go directly to the feature functions, they might be better for like active learning scenarios where you're having data streaming in, for instance, like IoT or various types of biosensors, for instance?
I think so. But to me, I just a lot of analysis we didn't do, but to me, when this becomes forward processing, I should intuitively have better control of what I do about it, right? So then, if you are applying this to a specific scenario, you probably have a lot of things in your mind on how should I put in this neural net. Oh, no, you can. Yeah. Thank you.
So in your expression bxy minus pxpy over pxpy, it seems to me that you started with shared divergence and then you moved to total variation norm.
I skipped a lot of discussion on this. Under the local approximation, all of these L2 level divergence are the same, are equivalent. So you can change this into a chi-square divergence local of KL total variance. Any F divergence, when you only worry about the hash comparison.
Oh, I see. Understood. Okay, thank you.
So this PMI came out of the second order approximation you mentioned of mutual information that's centered at the product form. So which is the independent case, right? The product
right. So
So does this mean that the accuracy of this is mostly around that independence?
Yeah. That's a very good point. That's also the David Shea's question about this. He said, well, the local approximation, you're basically saying the XY model is closely to being independent.
Right.
And how could you predict anything? So we don't. That's a very, very good question. We basically say you can't predict it. Okay. Well, which is also the point. We are not trying to predict why. We're trying to say, so the example I always give is, suppose I give you I take one Netflix movie, I break it into two pieces. I give you the first half, I ask you to predict the next half. And I say, well, use 2 words to predict it. And no way, right? You can't take one video to predict that. But if that 2 words happen to be Forrest Gump, you probably predict the second half of the movie. You know every scene about that. Right. So meaning there is a clear notion of what's informative about your video sequence. But based on that, you can't really predict. Right?
So I guess I have a question. Maybe I need to draw on the board.
Sure.
So okay. Suppose I do a very straightforward training in the conventional neural network. So I have this input, which I call as X. And then I basically allow, so first I allow only one feature. So I have this, so I have X1, X2, all these inputs. So I can train only one feature, which I call as X1. And from X1, I have a Y1 hat, okay? And of course, I have a Y to be compared with. Okay, so I can do this neural network training, no problem, right? So then I get a F1, and then I fix F1, and then I add one more neuron, one feature. So I have an F2 now. And so when I train F2, I basically use the residue of this Y from this F1. So I use Y subtract this Y hat 1 as a residue to compare with how this Y2 has.
You're right away in real time coming up with improvement.
So that's okay. So I can do that. So I have 10 features now.
Here's the problem. We didn't put any constraint on what is Y, right? So
I agree.
Now when you subtract,
approaches are very different. So yours is more principled. I guess mine is more straightforward.
Well, you would probably be consistent with me if Y is real value and you care about the L2 approximation.
Yeah, so
Right.
that's the question.
that-
What's the connection?
That would be
between
that
the
would
two?
probably be the right thing to do.
Mhm.
But in my setup, Y pretty much can be anything.
You mean here I allow Y to be just the scalar?
Yeah, the Y
real
yeah, could be categorical, could be class labels, could be a the second half of your movie, right? Could be a video sequence, whatever
I
it is.
can make my Y that big as well.
But you can't use you can't subtract two movie sequence, right?
That's true.
Right. So the
that means I
subtraction.
need to create something that I can comparable.
Right. So the subtraction business was not good. So you in some sense, what we did is we just add instead of subtract. We said whatever is just predicted, and then let's add it to whatever you can predict with the second guy together to predict that. So that's sort of a prediction.
Interesting.
Yeah.
Kevin.
Yeah, actually, this is also related to Yinbing's question, but maybe a very naive one. So in your H-score network, right, I know you eventually you combine and train everything all together.
Yeah.
But it seems to me the network structure implies an order.
Yeah.
So how do you know, how do you decide the order?
So because the order, no, I think you're referring
Or
to.
maybe if you change the order, would it?
Yeah, then you will get different result, right? See, now this thing, yes, I did have a order. Yeah, so this guy was used in the first one, but also used in this F1 is used in the first one, also used in the second one, also used in the third one, also used in that. This last guy only is used in here. So because of this order, you end up having put heavier weight on this F1. So F1 come out as the most significant feature pair.
Yeah, I understand that, but how to decide the order? My question is.
Well, so there is always, so this is like a SVD, there is always an order. There's always the strongest one, the second strongest one, the third strongest one, right? This order doesn't necessarily mean anything that we can describe with language. But between X and Y, there is always the strongest one, the second strongest one, the third strongest one. So what we basically use the network to separate this order.
It'll find itself, right? I mean,
Yeah, it would find itself. So
Finding
when this converge, this will be the first, the first pair of singular vectors with one every single value. This will be the second.
Yeah, so I think we're already over time, but maybe the last question.
Oh, just a quick question. So do we make this want to act as the same architecture in practice or not? That different?
When you,
I mean, like here, like it's a laptop.
well, in this one, right? Well, you can do whatever you want to do, right? So I'm not just specifying what network you want. You want to put in here. Well, when we use this to actually solve the ordered SVD, we did use the same network structure.
Okay.
Yeah, maybe just to check, is there any questions from online audience? We need to give them some opportunity to ask questions.
Let me keep showing my GitHub page.
Yeah,
I wrote a lot of this.
we were,
Not with me.
oh, okay.
input data X, instead of being just raw data, we can also embed it,
You can do
embed it in some geometrical space.
So you definitely can.
And have more.
If you
geometry.
know,
Like, yeah, exactly. Like graph. Like,
Yeah, okay. So let's thank Lizhou again.
Thank you.
Also,